All right, so good morning. I'm Floriana Petrone, assistant professor at University of Nevada, Reno, and visiting faculty scientist at Lawrence Berkeley National Lab. And today I'm going to give you just an update about the status of the research activities we are just conducting within the project, probabilistic simulation-based evaluation of the effect of near-field spatial evading ground motions on distributed infrastructure systems. The team working on this project includes myself, my PhD student Arsam Taslimi, who gets all the credits for the modeling and the simulation results I'm going to show today, and co-PIs Norm Abrahamson from UC Berkeley and David McCallum from UNR at Lawrence Berkeley Lab. I also want to acknowledge the collaboration with the DOE exascale computing project that is providing the computational capabilities for performing these regional scale simulations, and Dr. Roger Nkarka for providing the actual simulation results. Now, before getting into some details about, just what we are just doing, what we've accomplished so far with this research, just a brief reminder about the motivation and objective, overarching objective. So the main goal of this project is to develop an ability to utilize advanced simulations to fully characterize site-specific near-field motions for the seismic risk analysis of distributed systems, with the final idea of providing the basis for a comprehensive assessment of the risk posed to the distributed system as obtained from probabilistic seismic analysis-based approaches with use of catalogs of historical records and simulated records. And as a whole, this is motivated by the awareness that we know there are limitations associated with the use of target spectra when we want to evaluate the risk posed, especially to distributed systems. We know that when we use spectra, target spectra, there are just features of the ground motions, important features we miss, including the multidirectionality of the motions, the path-like component, or the site-specific variability. And so with this study here, we really want to look at just a closer look at these characteristics of the ground motions and understand to what extent this can influence the evaluation of the structural risk. Now, we have utilized, as you can see here, the San Francisco Bay Area as case study region and the West San Francisco Oakland Bay Bridge as the case study structure. So the project as a whole counted just three core components, elements. So the first one has to do with the construction of a database of validated simulated records for the San Francisco Bay Area, with the final identification of the just suite of ground motions that would be and have been utilized for just performing the linear time history analysis. And second element, development of a detailed finite element model representative of the Bay Bridge and in open seas, and then the execution of fully nonlinear time history analysis under the identified suite of records. And then finally, the evaluation of the demand distributions as obtained from catalogs of historical records and simulated records. And finally, also the assessment of the seismic risk after incorporating all the uncertainties associated with the structural model. So far, we have just completed core element 1 and 2, and just on core element 3, we are currently working on the incorporation of the uncertainties into the numerical model. Now, I will just briefly walk through all these elements and what we're trying to just summarize what we've accomplished, what we have done. And then I will spend some time talking about the just recent results from our nonlinear dynamic simulations. Okay, so for element 1, it's the construction of a database of simulated records. So some of you may remember that we started with the idea of having just 3 realizations, then we moved to 8, and now finally we have 15 realizations of a magnitude 7 Hayward Fault strike slip earthquake event. The overall idea here was really to start having a sense of the aleatory variability associated with this magnitude 7 Hayward Fault strike slip event. And here you see a representation of the slip distribution for these 15 realizations. You can clearly see different from each other for the distribution of slip, for the location of the hypocenter, so the point of initiation of these ground motions. And they're also different for the just depth of the rupture plane, so for the Z-TOR. All these models share the just frequency resolution, which is 5 Hertz, the cap on the shear wave velocity, 500 meters per second, and they all utilize the USGS 3D model for the representation of the geology structure with topography. And so here, starting within this core element number 1, so we have developed and proposed, let's see if I can advance this. Okay, a first step methodology and corresponding acceptance or evaluation criteria, if you prefer, to develop some confidence in the use of these simulations in just engineering applications, just what David McCullough was mentioning just earlier. This methodology here, and we just leverage the collaboration with Norm Abraham, so from developing this just methodology, relies on the combined use of motion models and real records, and starts from a selection of population of real records consistent with this scenario we're simulating, and then moves towards just application-oriented type of analysis. And here, as an example, I'm showing the interperiod correlation for a conditioning period of 10 seconds, which corresponds to the fundamental period of the bridge deck in the just out of plane direction, so represented here. And this shaded here represents the boundaries of this acceptance criteria. So really just the idea behind this criteria is really to provide some objective basis for evaluating these motions. And really this should be just interpreted as something that we need to utilize as function of the application. So in other words, for example, in this case, we were really just interested in the potential contribution of a higher mode to the structural response of the bridge, a long span bridge, long period structure. And so that's why that's something we looked at just closely. However, this type of validation can be done in different bandwidths and with respect to just a number of intensity natures of engineering or building response proxies that we considered in this methodology. Now, talking about the ground motions and the application to the Bay Bridge, so then we started looking more closely at the ground motions as applied at the bridge piers. So here's an example. I'm showing the spectral acceleration for the three just components, longitudinal to the bridge, transverse, and vertical for this pier number 4. So the concrete pier in the just Bay Bridge. And we are utilizing for this analysis the outcrop motion. So we just had to map the just 3D USGS model, velocity model with the SW4 just grid, and we just basically just selected the motions of the first just available just rock stations in depth. And here just we started looking at the just between events variability and within event variability across this 15 final set of realizations. And really just here, just to give you a sense, we also looked at the spectral bandwidths of interest for the response of the bridge. And so it will be just clear by the end of this presentation. So at the beginning, we were really just focusing on just the bandwidth around the 10 seconds, which is the fundamental period of this structure. And we were looking at the power as well, which would be 3 seconds. However, then we had to realize that what is really driving the dynamic response of this bridge is the second period of vibration of the towers, but I will get to this in a second. So then talking about the just the structure itself, so we're moving from element number 1, so construction of a database of simulated records and validation of that database to core element number 2. So we and where is we mainly my student developed a detailed finite element model of the West San Francisco Oakland Bay Bridge in open seas, and this was supported by an extensive literature review we did to come up with the details about the boundary conditions and all the just detailing about the connections between the different components. And as a whole, now the model counts about 23,000 degrees of freedom and utilizes a combination of different elements from fiber sections to shell elements to rotational trusses with a pre-tension force applied to them to just represent the cables. And so here, I just wanted to give you like just an overview. We're utilizing for most of the components state-of-the-art materials implemented in open seas, for example, Stilo 2 for the towers and the decks, and then Concrete 2 for the actual just concrete components of the deck. But then also we had to tailor some of these elements to the specific properties of the bridge. For example, for the just impact material, so we started from a formulation available in the literature, the Muthukumar in 2003 and Trident in 2009. And we just based the calculation of our KT1, so say just the initial stiffness, to the actual stiffness provided by the tower when it's hit by the deck. And so then we back calculated the effective stiffness and the post-yielding stiffness. And so just to give you a sense what is the type of approach that we utilize for modeling the whole bridge. Now, how did we then verify after this big modeling effort that the bridge we were just be constructed, we modeled was actually reasonable? So we utilized the data just available just in the literature, mainly we just made reference to other just models available, but also to just field data. And also to just a report, OPAC, and some of you may remember that it supported then the work that was done for the retrofitting of the Bay Bridge. So what I'm showing here in terms of bridge response is before the retrofitting. And so we could, as you can see here, just quickly from these numbers, I'm showing the fundamental just frequencies here. And we could match pretty well what was just measured in field and also in terms of spectral, in terms of modal shapes from what was available in the literature and other papers. Now, well, so now we had the just full set of simulations and then the just full model, the linear model in open seas. And then we started looking at the nonlinear response of the bridge with the simulated, full set of simulated ground motions. So here, just on the left, I'm showing the just two components, horizontal components, a transverse to the bridge and longitudinal scale to the target spectrum, which corresponds, according to the H2 provisions, to just a return period of 1,000 years. And this spectrum, we're also incorporating the near field effect modification factors, which, as you can see, just tend to really just pull up the accelerations at long periods. And here on the right, I'm showing the structural response, the distribution, the statistics of the structural response. And we're looking here at the tower stock drift in the transverse direction, which will be the in-plane direction for the towers. And here the decks central drift transverse direction again, which will be the out of plane for the decks. And these red squares represent the median just values of the response. And then we have these bars here, black just lines representing the standard deviation. Now, a lot of observations we can make here. We started like making here when we just first looked at these results, but then we just utilized a lot of animations from each of these realizations. And what really caught our attention was the distribution we were obtaining in the structural response when compared to the distribution here, which is also an artifact of the scaling of the actual input motion of the spectral acceleration, once again, at the fundamental period of that structure. And so what we realized is that what was really driving, not in terms of just amplitude, but also in terms of variability of the response, was really just the input motion at these towers. And then the input motion, the motion that the towers were just transferring to the bridge, to the deck. And if you think this WT that I'm showing here, and here the red line represent the yielded elements, and same thing for the deck here. So we're looking here that a tower that has a fundamental period just in plane of about 1 second. And here we're looking at the concrete pier. So even when our just in between within event variability is very low, which is something we're just observing these simulations. So the actual motion that is transferred by these two piers to the deck itself is completely different, which is what we realize is driving the response of these decks and this big spread here in the response. Then what we did, just starting from just the simulations only, we compared the same response here as obtained from real records and simulated records. So what I'm showing here is the comparison of the responses obtained from the real record here on the left and the simulated records on the right. And we're looking now at a subset of motions, 7, once again, according to the H2 provisions, and which were selected based on the minimization of the error in just matching the target spectrum and scaling the target spectrum. We looked at the positive component of the motions following just a model proposed by Hayden et al. In 2014. And so we came up with a final set of 7 records for both. Now, if we just the response, if we compare the two responses for the central deck, is not really just surprising. We see differences, but still we see just pretty much the same, just a number of motions just leading, just taking the structure in a linear regime. What was really surprising was to look at the response of the towers in the transverse direction. And what's here, just for the real records, none of them, just of the motions, just brings the tower in the linear just regime, whereas for the simulated records, all of them just are just well in the linear regime. So when we studied them, just linking this to what we're observing in the spectrum, so what we realized is that for a structure like the Bay Bridge that is characterized by elements having just completely different just dynamic response, our just method of scaling and the method that is proposed is part of the H2 provisions is probably not the most appropriate one. And so what is happening here is that as a result of this scaling in this bandwidth, 0.5t, just 2t. So we are just scaling in this region, but we are then overestimating the spectral acceleration at t1, which will be the higher just period for the tower. And so as a result, what we have here, just for the real records, 1G at 1 second, but for the simulated records, this goes up to like 4, 5Gs, which is what is driving this response here. And so now moving forward, what we're doing based on this just results we're observing, we are just going to explore just different and more appropriate methods for just scaling integral motions, for analyzing the response of a long-span bridge, complex structures as the Bay Bridge we're analyzing. Moving forward, we are just going, as I mentioned at the very beginning, to incorporate the uncertainties associated with the material properties into the OpenSys model. And so we're most likely going to use the COFAM just tool in the Sim Center to finally generate just probability functions for just that represent both approaches. The approach that utilizes the real records from worldwide catalogs and the simulated records, and to finally provide a basis, just a risk-informed basis for this type of comparison, and understand to what extent we can utilize simulated records and what can really add with the utilization of these arrays of simulated records. And with this, I just conclude my presentation. Here are some references for just in case you have any interest, and I'll be happy to take your questions.